When we start looking at polynomials and polynomial functions, first thing we're going to look at is what does a polynomial graph look like? The definition of polynomial should have come up in Algebra 1, where all the exponents are integers. So specifically here, what do graphs of polynomials look like? They are smooth and continuous. Smooth and continuous. So a smooth and continuous graph might look something like that. That would be the graph of a polynomial. The key is they cannot be discontinuous. And we looked at the types of discontinuities before, specifically something like a jump, like that, would not be a polynomial. So that's not a polynomial. And they also can have, or they cannot have, sharp corners. So for example, the most common example is something that comes down and then sharply goes back up. If there are any sharp corners, or what we call cusps, then we do not qualify it as a polynomial graph, and it can't be modeled by a polynomial. So the key is that my domain is always going to be negative infinity to infinity, and I have a nice, smooth, continuous graph. When we start talking about even degree functions, specifically here polynomials, they can fall into one of two categories. They can fall into the even degree or the odd degree. Remembering degree is just the largest exponent I have. The even degree all can be represented by x squared. They're all going to be similar to x squared in some way. And if I have an even degree that's reflected, it's going to be similar to what a quadratic reflected looks like. So I like to think of those as my representatives of even degree polynomials. When I think about odd degree, my representative I think of is a cubic function. So every odd degree polynomial is going to have something in common with this cubic. And every reflected odd degree polynomial is going to have something in common with that reflected cubic graph. So those are my base examples. And if I come down here and I look at these, traditionally we go through and graph them on some sort of graphing software, but I'll just give you the graphs here. I have x squared. Now I'm doing a pretty zoomed out picture. Some weird things happen between 0 and 1 on the x-axis, but I'm just going to show you in general what happens to these shapes. So there's x squared. As I increase the power up to x to the 4th, I have a lot in common, but I just get a little bit skinnier, more narrow in my graph. And if you can kind of guess, x to the 6th is going to have a lot in common, but it's just going to be, again, more narrow. And we could keep going with x to the 8th, x to the 10th, and so on and so forth. Every even degree polynomial is going to share this sort of shape. And specifically, eventually here, we're going to look at end behavior. They all share the same end behavior. On the other side, if I have a cubic function, there's my x to the 3rd. Again, I'm doing a pretty zoomed out picture. I'm not worrying about the weird things that happen with the fractional x values. As I start to get higher powers, my graph just becomes a little bit more vertical. So I have an x to the 5th there. And x to the 7th is again going to be a little bit more vertical. Let me grab a different color. There we go. So that's going to be an x to the 7th, and we can continue like that. The key is that every odd degree polynomial is going to share this same sort of end behavior. No matter what the degree is, as long as it's odd, it's going to fit into that part of my function family. So to summarize a little bit, if I have end behavior of even and odd degree polynomials, we saw that the distinctive feature is that we have this end behavior between one side and the other. So if I start by looking at the even degree, remember my representative here is x squared. If I have a positive leading coefficient, I'm going to describe the end behavior as up, up. We could write it with limits, but in this case I just want to get a nice easy graph of up, up. Negative, so reflecting it, is going to give me down, down. So this is every even degree polynomial has either up, up, or down, down as its end behavior. So I like to think of it as same. They both go the same direction. When I look at odd, I have my representative graph I like to use, which is cubic. odd is going to be opposite. 1 points one direction, for example, down, up, for the normal positive leading coefficient. Up, down, if I reflect it. But the key is I have opposite. So even degree, same, odd, opposite. If you remember your representatives, you can just base everything off of them, because everybody else behaves like those in terms of end behavior. Looking at a couple examples, we're going to go through identify the degree, the leading coefficient, and then we can say what the end behavior of the graph is. So for the first one, my degree is 3. My leading coefficient here, all that matters is he's positive. So I have a positive odd degree, and if I check out my chart or think about it, I'm going to have end behavior of down, up. I don't know what happens in the middle of the graph, but when I go left, I go down. When I go right, I go up. For number 2, I have a degree 2. That's an even degree, so I'm thinking same. It's either up, up, or down, down. And my leading coefficient is negative, so it's down, down. Number 3, degree of 5. Since it's an odd degree, I have opposite end behavior. Leading coefficient is negative, so I have up, down, because it's reflected of what a normal cubic or any odd degree polynomial would look like. Number 4, it's a little trickier to see. To get the degree, you have to look at what I would get when I would multiply and FOIL this all out. I'd end up with a 6x to the third as my first term, so the degree is 3, and the leading coefficient is positive. So odd means opposite, and I have down, up because it is positive. It hasn't been reflected. Lastly, when I look at this guy, I've got a third power, a second power, and a first power, which all adds up to a 6-degree polynomial. And if I multiply these guys out, I have 3 to the third times this negative 2, which just gives me a negative number. That's all that matters. I'm a reflected even degree polynomial. Since it's even, it is going to be same. And in this case, since it's reflected, it's down, down. So we're getting a good idea of what my graph looks like in terms of the end behavior, but not so much what's happening in the middle of my graph. The middle of the graph can be defined by this idea of turns. We're going to define a turn as extrema. In other words, any absolute or local maxes or mins are going to be counted as turns. A turn, if you think about it, is where the graph goes from increasing, which would be that portion there, to decreasing, right there. So I'm going to call that a turn, or vice versa from decreasing to increasing. So turns are where my graph goes and switches its increasing and decreasing, or you can think of them as the extrema. So if I look at my examples here, I want to sketch a degree 3 with 2 turns. If I see degree 3, I'm thinking opposite end behavior, because it's odd. Odd is opposite. So I might just go ahead and say, okay, there's my opposite end behavior. Now let's fill it in. If I come up, if I get 1 turn, I'll identify them there. And then I'm coming back, and if I get a second turn, I can identify them there. And that works out well, because then I am going in the right direction to meet my end behavior requirement. So there's a sketch of a degree 3 with 2 turns. There's other sketches we could make, but that's a pretty good one. Degree 4, that's even. Even makes me think same, and it could be down, down, or up, up. So I'm going to go ahead and make it up, up. So there's up, up, and now I need to have 3 turns. So I turn once, there's 1, I turn twice, there's another one, and hopefully my third turn will take me right back up, and he does. So I can have a degree 4 with 3 turns. Next one is a degree 7 with 3 turns. So degree 7 means opposite end behavior, because it's odd. So I start there and there. And then I try to start getting 3 turns out of this. So I come up, I make 1. There's 1. I make 2. There's 2. And I run into a big issue here because the third turn is going to take me back down. But I want to end with my end behavior going up. So no matter how many times I try this, and no matter what ways I try it, I'm going to find that it is not possible for this to happen. 3 turns is going to send me back to where I started from. So it's not possible to have degree 7 with 3 turns. We'll make a note of that here in a little bit. Degree 6 with 5 turns, a degree 6 is going to have same end behavior, so up, up. And if I put my 5 turns in, it's just a lot of wiggling. 1, 2, 3, 4, 5. And it doesn't matter how high or low they go, I'm going to get what I want out of this. 3, 4, 5. So just to make a note, we saw here in this middle example, and I'll try to solidify it here. If I have an even degree, then I have to have an odd number of turns. And if I have an odd degree, I have to have an even number of turns. And then one other fact, and this is just a fact that we have to believe. I can show you why at another time if you want, but the maximum number of turns that any polynomial can have is 1 less than the degree of the function. So putting that into a little bit of an example, if I have a degree, let's say 10, then the turns I can have are maximum of 9. And then if I put together what I've learned over here, it has to be an odd number of turns. So I could have 7, I could have 5, I could have 3, I could have 1. Those are the only options I have for a degree 10 polynomial. If I change that a little bit, think of it maybe as a degree 6. Nope, let me change it to a different number. Let's say degree 5. There we go. My maximum number of turns would be 4, or I could have 2, or I could have 0. A little hard to imagine 0 turns, but we'll see it here in a second. Those are the only options for a number of turns that I can have. A couple quick examples here of sketching. If I'm a reflected cubic is going to be up, down. We've seen that. And I have no turns. My graph is going to look a little bit like that. Reflected cubic with no turns. A reflected quartic, well, it's going to be down, down. And can I have 3 turns? Well, if it's a degree 4, I could have 3 turns or 1 turn. So I reflect, I come 1, 2, 3. And then I can point those out. 1, 2, 3. Over to my next example, I want a degree 6 with 3 turns. So if my degree is 6, I could have 5, 3, or 1 turns. So I know degree 6 is probably up, up, because it doesn't see differently. So there would be a degree 6 with 3 turns. 1, 2, 3. A reflected degree 9 with 5 turns. Well, reflected degree 9 would have to go like that. And if I think about degree 9, I can have a max of 8 turns, or I could have 6, 4, 2, or 0, but I can't have 5. So I'm going to say this is not possible. 2 quick examples at the bottom in our last minute here together. If I want to list if it's an odd or even degree polynomial and then state the minimum degree. Odd and even is based on end behavior. So since it's same end behavior, I have an even degree. And the minimum degree is going to be based on the number of turns. So if I have 3 turns, that equates to a 4th degree minimum, because the maximum number of turns, 3, is 1 less than the degree. Same idea here. I have down up, I have opposite end behavior, so it's an odd degree polynomial. And since there are 1, 2, 3, 4, 5, 6 turns, I have a minimum of a 7th degree polynomial. So there's just some basic introduction looking at end behavior of polynomials and turns. This gives us a good idea of what a sketch of the graph would look like, but we're going to go through and look at a lot more in terms of specific points to get a more accurate sketch in the future.